So again, my question is, why is ABC an inscribed versus a central angle? That's what I want to know. All right, 16. Why is that an inscribed angle? Okay, why is it inscribed then? So I could do an angle like this, and it would be inscribed? Thank you. That's what I'm looking for. The vertex is on the circle. Everyone good? All right, what's the rule then? How do I find angle ABC? It's equal to blank. This is the basic stuff here. 5, it's equal to, which in this case would be, what's its arc? AC, so half arc AC. Everyone good? Basic right there. Inscribed, half its arc. All right, then we went on to another fact about inscribed angles. Which angles are congruent up here? Do not give me the vertical angles. Taking that steam away from you. Which angles are congruent up there? And again, we went through this fast, so this is why I'm slowing it down right now to let you guys know what you're responsible for. 11, got another pair of angles that are congruent? Angle E and angle G. If you wanted to say that in a proof, here's what I would be writing. What type of angles are E and G? Inscribed angles. They're inscribed angles. What arc are they both drawn to? The same arc, DF. So I'd say inscribed angles drawn to the same arc. And what'd you just tell me about them? Are congruent. All right? That's a fact we got to know about inscribed angles. If they're drawn to the same arc, they're congruent. Anthony, let's roll. Darn right you could. Same reason. Same reason. All right? I'm going to mix in the homework now because I want to show you where this came up for homework last night. Okay, everybody ready? 18, you had the evens, correct? 18s, yes? You had to find angle S. All right, so whether you did it or not, I have it up here already. Name 2 angles that are congruent based on they're drawn to the same arc. Name 2 angles up here that are congruent because they're drawn to the same arc. Here we go, 12. Angle Q is drawn to ST. Angle T is drawn to RQ. I need 2 angles that are drawn to the same arc. Everyone agree? Inscribed angles, S and T, drawn to the same arc, RQ. So they are congruent. So you needed to solve this one by doing 5x plus 4 equals 6x minus 2. Everyone see why they're congruent? Inscribed angles drawn to the same arc. Then you solve for x and you plug it in. All good. Going. All right. You guys know how there's a lot of stuff in this unit. All right, next one. Angle C is Y type of angle. That's real good English, right? Is what type of angle? Angles, and that's a diameter, by the way, here. AB that's the center. AB is the diameter. Angle C is what type of angle? I could get a lot of responses here, actually. 14, anything you want to say. Angle C is what type of angle? It's inscribed. Perfect. So I usually do half its arc, right? Everyone follow along with me. Angle C is drawn to this arc right here. What type of arc is this? That's a diameter. This is a what? Semicircle. Which is how many degrees? 180, half of 180? Angle C is a what? Right angle. All right, angle C is a right angle. Let's say that's in a proof. What would I write in my reasons? Ready? What type of angle is it? Before it was a right angle. Inscribed. Inscribed angle drawn to, what was it drawn to? Semicircle, or I'd accept diameter. I heard that. Inscribed angle drawn to a semicircle is what type of angle? Right angle. Okay? So if you see an inscribed angle drawn to a semicircle, it's a right angle. And there's the fact I would write in the reasons column. Everyone see a right angle in that diagram? Anybody see an inscribed angle drawn to a semicircle? Name it. Name the angle. 24, name it. Where's the inscribed angle drawn to a semicircle? Angle S. It's a right angle. So what are you going to do with these two then? What's your goal? That was on the homework. 21, what do you want to do with these two angles? Equals, sorry, I didn't hear the rest of it. Equals $1.80. Good. You solve for x and plug it back in. Yes? You could. That's the other way around it. Yep. You could do 3x equals 90. Look at that. Yes, John? Say that again? 4x? Oh, because okay, so you doubled this and said that's 4x. And then you doubled this and said that was 2x. Okay. All right. And everybody all right? We good? Guys getting clever on me here. Billy?
I just did 2x plus x equals 180. I didn't put the 90 in.
Equals, but they don't equal.
And I just got 60.
For x equals 60, but it's looking for angle T, which is 60. But if you plug in 60, you get 120 for that angle. But it's not 120, it's 60. So x can't equal 60, it's got to equal 30. Okay? What's that? Yeah, that's fine. Yeah. We all right there. Biggest thing, inscribed angle drawn in a semicircle is a right angle. And there's one more fact I went over literally when the bell was ringing, so I want to make sure we're clear. Four-sided figure, quadrilateral inside a circle. The opposite angles are, so name two angles up here that are supplementary. Angle A plus angle C equals 180, and angle B and angle D add up to 180. Only for a quadrilateral, that's it. Only for a quadrilateral. Okay, your turn now. Tell me two angles that add up and set equal to 180 in this quadrilateral here. I got RTZW. Name two angles that add up to 180 in this diagram. Here you go. Let's hear from 15. Name two angles that add up to 180. What is it? You got it. Yep. 2x plus 30 plus 4x equals 180. Yep. And then you guys solve for x. You had to find angle z, so you plugged it in. Okay? That's a lot about inscribed angles. Okay, I'm going to go through it again. Ready? How do you find an inscribed angle? Half the arc. What if two inscribed angles are drawn on the same arc? They're congruent. What if I have one inscribed angle drawn to a semicircle? It forms a right angle. And then finally, if you have a quadrilateral inside a circle, what do you know about the opposite angles? Supplementary. There it is right there. Those four facts. Okay, those four facts. 22, I threw a proof at you. Not too sure how many people tried it, but we're all going to try it as a class right now. What's the only method we have to prove them similar? Yes?
Quadrilaterals are always 360 degrees.
Inside, yes. Inside. What's the only main method we have to prove triangles similar? Angle. So I'm gonna, I don't know, can you see this? We all right? Do I need to blow it up? We could see this all right? Because I'm gonna ask somebody right now, name a pair of angles that are congruent. Because I need to get two pair up here. And I don't care which pair you pick up here. Name a pair of angles that are congruent. 10, what? Name two pair or a pair. Okay, so I have angle J congruent to angle K. And I know one is usually the givens, but We just went over this theorem. Why are J and K congruent? 7, what do you got? Great job. 3. Okay, hold on. They're what type of angles first? Here you go. Inscribed angles. Drawn to the same arc are. Well, I could also put what in the same statement? I could also put angles H and L. And then why, if you put these in there, why would these be congruent? Vertical angles. And then the triangles are similar by angle. So not a long proof at all. I just want to make sure we're clear on that. And the other one I picked out to do with you guys was number 16. Number 16. Find angle S. All right, a couple people are going to help me out here. First off, 23. What type of angle is angle S? Inscribed. Yep. So I know the rule is it's half of an arc. Name the arc I'm going to take half of. Not the degree of it, just name the arc I'm going to take half of. 29. RT, yes. I did not give you RT, I gave you ST, but how can I use ST to get to RT? 2. Subtract it from 180 because this is a what here? Diameter, that's a semicircle, yep. So that's going to be half of whatever 180 minus 48 is. And that's how we got the 66 degrees. Okay. Whew, a lot there, guys, huh? Going into quiz 2 already. Anything else you want to ask from the homework that I did not go over? I know I went over a lot. Not all of them, though. Anything else? Okay, I'm just going to walk around and see what you did. You know, I'm just looking for some effort. Okay, if you're missing 2 or 3, I'm probably not going to notice, but you'll get your 3 points, I guess. And as you guys will find out, it shows up on the quiz quickly. Hello, gentlemen.
Good morning.
Good morning. Not bad there, superstar. You'll find out later, not bad.
Okay.
This whole group, not bad. Well, except for the omitted one. Got it. Where were you this morning? Okay. I'm glad you're back, yep. When are we going to take the quiz? Before the end of the week? Yes, we can. Okay. I already came over here, didn't I? Yeah. Thanks. You're going to... That one I saw you struggle with? You just had to draw in the other... Remember I gave you the radii was 8? Just draw in another one that made a right triangle and you could have done Pythag. Okay.
I knew something.
Overthinking it. Overthinking it. All right, let's go, kids. Here we go. I know I say this every day, but yeah, it's going to be new terminology today. That's why this unit's difficult. New terminology. A tangent. And it's not the same tangent as SOHCAHTOA. All right, totally different here. Here's what a tangent is. A line that intersects the circle, one spot only. One spot only. So does everybody see I have 3 tangents going on in this circle here. Touches it in exactly 1 point. See that? Let's talk about this right now. That point where it touches has a special name. So F, C, B, they have a special term to it. And let me tell you, these mathematicians are pretty clever. The point where the tangent touches the circle is called the point of tangency. I know. I don't know if there's an EY at the end or a Y, and personally, I don't care. So. Go over my second diagram. Can somebody, I need a bunch of people, help me explain why these are not tangents. Why is RS not a tangent? Doesn't even touch it. What about PQ? Twice. It's got to touch once. Touches it once. Hey, whoa, whoa, whoa. Whoa. TU, that touches it once. It's got to be a line. And if I extended it, what would happen? It would touch twice. Same thing with WV. It's a ray, not a line. All right, it's got to be a line that intersects it in one spot. Good? All right, not too bad. All right, here's the challenge I love every year. Common tangents. Okay? How many lines I can draw in? All right, that touch each circle in exactly one spot. So when two circles interlock like I have here, I'm claiming there are two common tangents. Where are they? You can draw one line that intersects both circles in exactly one spot. And there'll be two of them in this case. So let me show you what I mean. Give you a little demonstration. Boom, there it is. There's one. I'm claiming there's two in that diagram. Where's the other one? Remember, it only can hit each circle once. Where's the other one? Where's the other tangent? On the bottom here, yes, yes. Okay. Yeah, Billy.
So, like, you couldn't draw a line between them, like this.
Because it would hit twice. If you draw a line between them, it would hit one of the circles twice at least. Yeah, you ready? You see this line right here? Hits this smaller circle once, hits the bigger circle once. If I draw in any other line anywhere else, it's going to hit at least one of the circles in two spots.
So, like, that little piece in the center, like, you couldn't draw it there.
What little piece here?
Like,
But it's hitting the smaller circle twice. It's got to be a full line. I got to be able to extend it. Okay? All right, here we go. Now they're separate. And I'm claiming there's four tangents. Where are they? What's up, Emma? I don't know. Could I? So you want one right going this way? There's one. You got three more for me. Going the opposite way. Yep, here. Two. Three. Four. I'm not going to tell you now. What if the circles are just touching? How many common tangents could I draw in? I'm hearing two and I'm hearing three. All right, where's one of them? Well, first of all, let's get it out of the way because we know top and bottom. So definitely two. Some people are saying three. Where's the third one? If these are just touching in one spot, yep, there it is. And then a circle inside a circle. How many? Just the one where they intersect. All right, I got a quick challenge for you. We've gone over one. We've gone over two. We've gone over three and four. What would it look like if they did not have any? No common tangents. What would the two circles look like? Concentric, yes.
Oh, that's what.
Right? Everyone agrees those two would not have any. All right? All good. All right, well, we got to learn something about these tangents other than these beautiful lines everywhere. All right, I already discussed the point of tangency. That's the point where the tangent hits the circle. What I'd like you guys to do with this next theorem, you got some space in the top right-hand corner, right after the point of tangency definition. Draw a circle up there for me. Draw a circle right up in this space right here. I got more space down below, so I'm just going to cheat and do it down here. And what I'd like you to do is draw a tangent to the circle. One tangent line. There's infinite many here you could draw. All right, there's an infinite amount. Draw one tangent line for me. Name the point of tangency, whatever letter you'd like. Put a center in your circle. Put a center in. And draw in the radius to point to the point of tangency. Draw in your radius. Here's the first theorem about a tangent today. If you draw a radius to the point of tangency, go ahead and read your theorem. What's happening here? What is happening on my diagram that I can now add to it? It is perpendicular. All right, so if you draw a radius or diameter, whatever, a radius to the point of tangency, those two are perpendicular. They form a right angle. Okay? All good. All right. Number one, find angle x. First, ready? This is going to, every day. Is angle x, is that a central angle? No. Is it inscribed? No. So none of those rules apply. But what did we just figure out? I got a radius drawn to the point of tangency. What type of angle here? A right angle. And then hopefully we know how many degrees in a circle, in a triangle. 180. So 180 minus 90 minus that 58. What are we looking at here for angle x? 19. We have a 19 in the house. 32? Thank you. All good. What's another thing we usually use with right triangles as well? Oh, yeah, speaking of Pythagorean Theorem, here you go. Take a look at 2. Anybody want to add to the diagram? 18. Anything you want to add to the diagram? A right angle at point, which vertice? B. Yep, I got a right angle here. Radius drawn to the point of tangency. Pythagorean Theorem. Here we go. 9. What are the two legs in this? So x squared plus 8 squared. Uh-oh, everyone ready here? 20. Name the hypotenuse. How long is the hypotenuse? Nice. How am I going to write that in Pythag here? Parentheses x plus 2 squared. Yep. So x squared plus 64. I cannot let you leave geometry in June without knowing what to do here. It's not x squared plus 4. My heart, as small as it may be. What do you have to do here? X squared plus x plus 2 times, there we go, little double distribution here. I'll ask somebody in a second what they got. Oh boy. 6 there. What'd you get when you double distribute? X squared. Thank you. Plus 4x plus 4. Yeah. Everyone good? What's going to eventually happen here? I got x squareds on both sides. They're going to cancel. Move one over. They're going to cancel. Everyone see that? So all I'm really left with is 64 equals 4x plus 4. Solve that beast for me real quick. Oh, 23. Hi.
X equals 15.
Thank you. Please don't go ahead. We're not going to do number 4. We're not going to have the time, so I'm going to skip over it, but I am going to do number 3 right now. Where's my right angle? First of all, where's my right angle? 30. Good job. 6. Where's my right angle? Angle B is the right angle. What is that? It's not a right angle. There it is. 26. No? Oh, Jack. I keep forgetting. Sorry, boss. Name one leg of this right triangle. X. All right. X squared. Uh-oh. I didn't give you the other leg. I didn't give you CB. Let's think. Come on. Dig deep. We're not putting an X there either. You know the value. CB. You know the value of it. What do you got for me? Oh, 10. CB is a radius, and I've already told the radius in that diagram is 3. And then the hypotenuse, 11. How long is the hypotenuse? 10 squared. There you go. X squared plus 9 equals 100. Oh boy, how many people are doing x squared equals 81? Stop being an embarrassment. 91. People do 81 because they want to hit that perfect square. And I'm just going to have you guys leave it as the square root of 91 because it can't be broken down. All right, I'll leave it there. All right, we'll save 4 for another time because, whoa, yeah, look what's coming up next. Get up, here it is. Proof time. Prove BA congruent to BC, and those are tangents here. Before you prove those segments, what are we going to have to do, kids? Oh boy, crickets. Yes, prove the triangle so I can do a little CPCTC on everybody. All right, let's get the triangles congruent. Got to get the triangles congruent. All right, anywhere you want to start. 21, anywhere you want to start. Whoa, that's hardcore. I like it. Wow. Like it. Angle A and angle C are right angles. Nice. Went for the throat right away. I love it. Okay, the reason. Here we go. Ready? It's a new one. I don't want to write all that. Neither does your classmates. Trust me. I've seen some of it. All right. What is it? We're ready. What's BA? Is a tangent. And what is OA? So ready? Radius drawn to. What do we call point A? Radius drawn to. Point of tangency is what? Perpendicular to the tangent. Yeah, I know it's a lot. Sorry. Cry me a river. Radius drawn to a point of tangency. Now, do I need that word for word? No, I'm pretty flexible, but If you do your own hieroglyphics here, not going to be feeling that. All right, thanks, Emma, for the right angles. Need something else to get them congruent. 8. Anything else I could get them congruent? Oh, don't have one. Never have we had one. Great. Well, we may have had one. 18. Anything else to get the triangles congruent? Sides or angles? Oh, of course, right? Got to throw that bad boy in there. A little OB. Okay. Am I done with the proof, Jack? Yeah, why don't you calm down, boss? Okay, I'm the reason I got the pen up here. All right, there's a reason. And I am just going to sit you down in about 2 minutes. All right. You didn't want to say that, Jack. All right, didn't want to say that. What else can I do here? I got the side. I need something else, though, right? Need something else. Where's the something else here? It's a circle fact, aka it's a circle fact. 23. Where else can I go here? Come on. AO. Congruent to OC. Why? Okay. You can thank your teammates there. In a circle, all radii congruent. Side angle side. Excuse me. First of all, there is no such thing as side angle. Not even in week 25 of the school year. This is not side angle side because the angle's not in between. Hello, Emily. But it is what? Ready? Hypotenuse. That's your reflexive side. Good job, Emily. And the L is the radii. If I'm doing an HL proof, do I need to say the angles are congruent? No, I don't, Jack. I don't. So I'm not even going to say it at all. Okay, that's how I knew it was an HL proof already. But hey, you want to go and impress somebody who I don't know, go ahead and write it in. It's an extra step that's not needed. Okay? But hey, in all seriousness, do we see the HL? Can't write HL yet. Review here. Got to tell me they are right triangles. All right. So triangle AOB and triangle COB are right triangles. Anybody remember the reason or have a good reason? Right triangles have right angles. And now you guys have 2 more steps to finish it. Now tell me they're congruent. By HL, and then yes, a little CPCTC. I don't even know if I just said that right myself. BA congruent to CB. Okay, 2 reasons why we did this. One, it's always good to do a proof, specifically an HL one. Second reason, you just found out a new fact about circles. You just found out a new fact. What were A, B, and BC again? Tangents. And they're both drawn to the same point. Everyone see that? B. So if you ever have 2 tangents drawn to the same point, what did we just find out about them? They are congruent. A lot of kids, and I would never, ever, ever accept this in a proof, a lot of kids call this the party hat theorem. The party hat theorem. Okay? No. The party hat theorem? Okay. All right, hey, now, oh, you drew in the eyes now. Now I see it. Yeah, now I see it. Yeah. Got a little crazy at the party, all right? All right? Got a little crazy, got a little nuts at this party. All right, I want to show you where this party hat theorem can be used now. We're used to the polygons being inside the circle, but now it's outside, circumscribed. And I want to find the perimeter of each. Perimeter, all sides added up, right? So we already know what? One side of this is 7 centimeters. We just got to find the other two sides. And we're going to apply this theorem. If you draw two tangents, ready, watch. I think I can do, yep. See that? Two tangents drawn to the same point on the outside. What's this distance here? 4. They're congruent. That's 4. And I'm going to go all the way around the circle now. Ready? Over here. Everyone see two tangents drawn to the same point. So what's this segment here? 5. So it looks like one side is 9. And what about that third side? Everyone seeing it here? Two tangents drawn to the same point. So this missing piece is 3. The other side is 8. For a total perimeter of 24 centimeters. The old party hat theorem. 6, here we go. Oh, this one looks pretty easy, right? I got 9 already. I got 8 already. How about that third side? I'm going to have to do a little work here. 5, you're on this, Fiona. Ready? 6, this one's going to be 6. What about this piece? 3, because it adds up to 9. This piece? 3. This piece? 5. This piece? I don't know where 10 came from, but that side's 11. I didn't think so. What are we looking at for that one? 28 inches. Let's go. Let's go. What about that angle there? Remember everything we've done today. Is it a central angle? Angle X, sorry. Is angle X a central angle? Nope. Is it inscribed? Nope. So I'm going to have to do something different here. Anything else you can add to my diagram based on what we've done today? Right angles, yes. A radius drawn to the tangent forms a right angle. How many? 2. All right. How's that? How's you? I don't know. Okay, I got 130, I got 90, and I got 90. How's that going to help me? Yes, Thomas, because you asked the question earlier, so I hope you know this. There's a quadrilateral in there. How many degrees in a quadrilateral? 360. So x can be found by doing 360 minus 90 minus 90 minus 130. $50 degrees. And then finish it off here. This has absolutely nothing to do about tangents because there's none drawn in the diagram. I gave you that angle's 50. I'm looking for that top angle. This is a little review. No 90-degree angles here. What's up, Catherine? So what? Oh yeah, the radii are congruent. What type of triangle is this? Isosceles. So the other angle is 50. How can I find angle X now? 180 minus 50 minus 50. I end up with 100. Nope. 80 degrees. All right, keep bringing it here. Keep bringing it with your effort. Most of you keep bringing it. I'll put those grades up sooner or later today.